So far, we have looked at general purpose microcontrollers like PIC and ARP. And these microcontrollers, in their instruction set as well as internal architecture, there were enhancements to support signal processing operations. Today, we shall look at processors which have been designed specifically for signal processing applications. Now, why these signal processing processors are important for embedded systems? In a way, embedded systems are targeted for what we call situated computing. An embedded system is situated in an external environment. It receives input from external environment via sensors, and the signals that it receives through sensors are processed for taking action via actuators or doing some kind of communication or data processing task. Now, sensors can be designed for virtually every physical and chemical quantity, and in fact, today there are a variety of sensors available which can be interfaced and used in your embedded systems. And all these sensors provide you with a set of discrete values which needs to be processed. Although many of these sensors work in analog domain, I need to do what? Convert this data from analog to digital form to do any kind of processing. We shall look at some example sensors. A very common example is your CCD sensors, which are used in camera for sensing images. In fact, either CCD or CMOS sensors you will find in your common digital cameras, which is very commonly used embedded system. The CMOS sensors you will find on your cell phones. So these sensors are for sensing images. We are looking at, in particular, CCD sensors, which is a light sensitive solid state silicon device composed of many cells. These cells are actually nothing but some form of capacitances which accumulate charge depending on the intensity of the incident light. And at each site, this charge, which translates to current, is integrated over a period of time to get a reasonable signal to noise ratio. So you have really the data that you are getting represents external world and not the noise. And these charges are shifted out using shift registers. They are not digital shift registers, but shift registers for storing charges. So you have got something like charge buckets, and charge is shifted out sequentially through these buckets. Now, obviously, the output of this sensor is analog current. Okay, and this has to be converted to digital form using ADC to get the digital data, and this digital conversion has to take place at pixel rate. That means if we are taking frames at the rate of say 25 hertz, and if we are talking about an image size of say 256 cross 256, then there is a definite timing window at which we have to obtain data for each pixel per frame. So our analog to digital conversion has to take place at that rate. And subsequently, I need to process this data for any kind of operations. Another example of a sensor today which is becoming very common for security applications are these biometrical sensors. This is a sensor for taking fingerprints. Even today you will find products being announced that you may have a cell phone with a fingerprint sensor so that it becomes a unique access. So various such products are coming into the market. And this is an example of a fingerprint sensor which has got a matrix of 256 into 256 sensing elements which obtains the fingerprint. And here this is a picture of the sensor, and this is the kind of fingerprint image that the sensor provides. So obviously, to process these kind of data which are coming from a variety of sensors, I've given just two examples, there may be hundreds of other sensors, we need special processing capability for the processors. So we are doing digital signal processing on the processors for process decided by the properties of the signal. And so digital signals typically obtained from physical signals via transducers and converted to a digital form using ADC. I have given you an example of how that image data gets converted, and then it is processed by a DSP, which is an electronic system that processes these digital signals. What are the features of digital signal processors? If you have seen the nature of the data that has come in, there will be repetitive numeric computations, because if you consider an image, there is a pixel coming from each side, sensing side. So, number of pixels is 256. If one operation has to be operated on a pixel, then I have to operate it 256 into 256 times. So, I have to do repetitive numeric computations. High memory bandwidth is required to transfer this volume of data, okay, because it's effectively, if you look at an image data 256 into 256, the standard representation is array accesses, because I am just having a sequence of pixel data. The numeric fidelity is also of importance, because I cannot really have errors in the computation. And the other requirement is real time processing, and this real time requirement is imposed by the nature of the signal. As I was talking about, that I have to obtain a pixel at a particular rate, satisfying the condition that I am taking frames at the rate of 25 hertz. And if I have to produce an output image at a particular rate, then my processing has to take place consistent with the sampling time period available with me. So, external signal imposes real time constraints. Now, all these things have to be done taking into account the overheads introduced by cost, power consumption, memory use and development time. You would definitely like to have minimum cost, and that attempt to minimization of the cost, you will find today, has resulted in having almost all cell phones coming with your image sensors, the camera, and your webcams available with your PCs at almost minimum cost. Power consumption also becomes important, because I won't like to do any kind of processing consuming a lots of power, because majority of my embedded appliances would work on battery. And memory usage, there is also a restriction. The restriction comes from the constraints of power as well as that of the size. There are many DSP applications. We have just listed some of them, and in fact all of these applications are actually put into some kind of a dedicated system, which are nothing but what we call embedded systems. Your audio coding, decoding, surround sound, say your MP3 players, okay, are all basically doing what? A decoding, decompression of the audio data. That means it is doing a signal processing task, and they are all embedded systems. Cellular phones we have already talked about, and which is targeted for communication, but it has to do signal processing because it is receiving your speech input, then converting to an appropriate form so that it can be communicated. Robots, any kind of robo, are example of embedded systems. Even your disk drive control, which needs to do some kind of signal processing, because it is sensing the position of that your head in the disk to get the data correctly. So, that is also an example of an embedded system, because that is not doing a general purpose computing. In the field of medical diagnosis, these diagnosis equipments, all of them are obviously processing variety of signals obtained from biomedical sensors. Your ultrasound machine, your MRI imaging devices, your ECG devices, they are all doing necessary signal processing. And defense, your radar and sonar processing, missile guidance are other examples which are uh, really doing complex signal processing tasks. And in fact, a typical a sonar processing board may have a number of these powerful signal processing chips sitting inside doing parallel computations. Common DSP algorithms will be filters, because we would like to remove noise. That is one of the objectives. Other objective is to look at different components at different frequency bands. So filters are very common application. Transformation, that is taking the signal from time domain to say frequency domain in case of speech signal. In case of image signal, we may like to transform from spatial domain to frequency domain. So these transforms are also very important algorithms. Then performing variety of correlation tasks for doing signal classification. It is also a very common operation which is done. Now, if these are the common algorithms, okay, then the basic question comes up is the DSPs, that is digital signal processor, must have dedicated hardware to facilitate implementation of these common algorithms. We shall look at the simplest of them, and with respect to that try to understand the requirements of the architecture and see how that is really realized in different digital signal processors. So the simplest one is FIR filtering. So FIR filter consists of multiple taps, and what is happening here? If you look into it, these are nothing but signal samples, and the D is just representing the delay element. And what is really happening is, I am doing at each tap, that if I look at these as a tap, at each tap what is the operation? I shall be doing two data fetches, a multiplication and an accumulation, and we would like to write back to the memory to do the subsequent computation. So what is therefore the requirement in this case? The requirement is I need to have the ability to fetch data. Okay. In fact, if I can do multiple data fetches simultaneously, that would help the implementation. Then next what we are doing? We are doing a multiplication, which is basically multiplying with the coefficient vector of the filter, and then we need to accumulate the data. So what we are doing is, this is a multiplication, h, one of these coefficients, we are multiplying with this, and then we are accumulating with what has been already done earlier. Okay. So what we are therefore looking at, we are looking at data fetch, multiply, accumulate, memory, write back. So let us see how it can be done. We are looking at one of the earliest digital signal processors. It was introduced in 1982 by Texas Instruments. Now here you will find that we were using Harvard architecture. In fact, there is a separate instruction memory and separate data memory. Why? Because obviously you have required that for each tap I require data fetch and multiple data fetches. So I would not like to have the bottleneck in memory data transfer. So the option and the choice has been Harvard architecture. Now if you look into here, you have an accumulator, a classical accumulator which participates in these arithmetic operations, and specialized instruction containing load and accumulate. Okay. So here let us look at these internal organizations and look at the data path. What you will finding here, that you have got a dedicated multiplier, because multiply has to be operated at each step in the FIR filter, and it is to be used with the entire sequence of the data. So, you have got a dedicated multiplier, you have got a separate register where you are getting the data and putting it from the memory, and output of the multiplier goes to something called a P register, which can be used with the ALU to get the accumulated result in the accumulator itself, okay, and that can be put back again with the multiplier if required. So, these organization, you can realize that this organization of the data path is primarily to facilitate multiply and accumulate operation, which is the key operation in case of any filter implementation, and we have seen how it is critical for FIR filters. So, let us look at the code, a filter code with respect to this processor. Let us consider these X4 and H4 are direct absolute memory addresses, and what we are showing here is I am loading T register we have already seen with a particular sample. I am multiplying H4 has already got a coefficient of the filter coefficient vector. So, I can compute when I multiply, I have got a P register below that of the multiplier block. So, that data goes into the P register, and then I have an instruction called LTD X3, so which is loading T with the next sample and also loading my accumulator with accumulator plus P. This can be done because these are at two different parts of the data path. So, effectively what is happening is, what I require just two instructions per tap, effectively just two instruction per tap, okay. And this has been possible, and this is possible because the organization of the data path which has been provided for. You can see that I can do a register, this T register load as well as accumulation through ALU to the accumulator simultaneously. So, you can understand therefore the demands of the processing and how it has influenced the design of data per design of the signal processors. So, with this motivation and the background, let us look at the other features which are common to most DSP processors. These are the points which are listed, and these are the features which are universally true for all these processors. Data path is specially configured for DSP. It has got a set of specialized instructions. There will be multiple memory banks and buses because you would like to have multiple inputs simultaneously. For this purpose, specialized addressing modes, some execution control techniques, and specialized peripherals for getting inputs from the sensors. I may even have, actually in many of these signal processor you have onboard digital to analog converters for the output and analog to digital converters for the input. So, let us look at the data path. We have already seen some aspect of the data path, and here we are trying to look at some of the other aspects. So, specialized hardware to perform key arithmetic operations in one cycle, and key operation is particularly multiply and multiply accumulate. You have got hardware support for managing what are called shifters. In fact, we have already seen barrel shifter in the context of ARM processors which facilitates multiplication, but shifters have also got another very important role in the context of floating point numbers. It can be used very easily for adjustment of mantices, because I have to make the exponent same by adjusting the mantices for doing any kind of floating point operation. Then many of these processors in their accumulators have got what are called guard bits, that means additional bits to increase the accuracy of the results, because you can understand that precision of a computation depends on the number of bits allocated to store the data each data element. Now, if we can have additional bits allocated, then what is the advantage? Advantage is the precision of the result increases, and if we are doing a multiple step operation, then the result, because of truncation or rounding at a particular step, will not accumulate, because I have allocated or I have got additional bits to store the intermediate results. So, you will find many of these digital signal processors, it may support say a 32-bit data word, but accumulators may be 40-bit and supporting 8-bit of GERD data to increase accuracy of computations. And this design comes from the requirements of numeric fidelity. Saturation we have already seen. The saturation instruction set in fact in that DSP extension of the ARM, so that there is no wrap around, okay, and this is important for delivering or managing the signals having values within logical limits. Therefore, what I was talking about with relation to the GERD bits is that of a precision. Precision is an important component for representation of a fixed point data, even for the fixed point processors. Precision is defined as the smallest step between two consecutive numbers that can be obtained for a given number of bits. And in fact, you will find that these fixed point processors, they use QM.N format numbers, okay, where N is the number of bits allocated for the fractional part, M for the integer part, and it is not really a floating point representation, it is a fixed point representation. Depending on the number of bits allocated, there will be the range of numbers that can be represented is different, and the most significant bit, that if I am having a 16-bit number, okay, so the 16-bit can be used also as a sign bit. So, depending on the format, the precision would change, okay. Therefore, you can realize that the word size is a critical component, and you would choose a DSP depending on the precision requirement of your application program. So, I have shown some examples that DSPs can have 16-bit, 20-bit or even 24-bit data words. On the other hand, you have got floating point DSPs as well. Obviously, floating point DSPs hardware wise will be more complex, their cost would be more, and in many cases they are also slower because of the clock speed restrictions, and they will obviously consume higher power because you are having more hardware on the silicon real estate. But floating point supports simplified development, because why this issue comes in? Because if you have to realize say a FFT or a DCT operation, any kind of transform operation using a fixed point processor, your software needs to take care of the precision issues, representation of the numbers, and obviously that may result in more development, software development time. The saturation is, we have already talked about, that in the data path you have got units, specific units, which sets a number to most positive value, prevents wraparound, and this is done using spatial arithmetic instructions. And we have seen for signal processing operations like operations on the pixels, I would not definitely like a pixel value to become arbitrarily 0 or beyond 0 to wrap around. If it is maximum, it should get stuck at the maximum. If it is minimum, it should get stuck at the minimum. The multipliers is definitely a key component, and a simple analysis of code have found that more than 50% of instructions can involve multiplier. And majority of these DSPs implement what are called single cycle latency multiplier. That means you can do a multiplication using a single cycle, and you have got multiply and accumulate instructions. So these are typically built as separate hardware blocks and not strictly part of the ALU. Next issue is related to these is that of rounding. We have already talked about precisions. Now, when we are actually doing this kind of real number arithmetic, say multiplication, multiply and accumulate, rounding becomes critical. Okay. Obviously, when we use guard bits, you are increasing the precision. Okay. So, when your accumulator is using 40 bits, you are doing accumulate with the help of 8 bit additionally available as guard bits, and your precision increases. But when that result has to be stored in memory, these guard bits have to be discarded because your memory is organized as a 32 bit data word maybe. So, in that case you need to do rounding. Typically you have got 3 schemes, okay, which are chopping, von Neumann rounding and normal rounding. In chopping, you remove guard bits with no changes in the retained bit. Okay. So, it is a kind of a biased approximation because you have the result biased up to the positive end. The other thing is that von Neumann rounding. What happens in von Neumann rounding? If the bits to be removed are all 0, then there are no changes in the retained bit. If any of the bits removed are 1, then LSB of the retained bits is set to 1. And you can understand this pretty well. The whole motivation is that you are obviously, if it's are all 0, then we need not do the change. If there is a some change, we are setting the LSB to 1. So, we are going to the, if the LSB is already 0 of the retained bits, by 1 we are moving toward positive. If it is already 1, we are not moving towards positive. So, there would be a negative error. So, it is a kind of a unbiased approximation. But obviously, the approximation error would be pretty high, okay, because what I am doing, I am changing just the last bit, that LSB, depending on the bits which are getting truncated. The rounding, the basic philosophy of rounding is round to the nearest number or even number in case of a tie, is an approximation technique which reduces or which has got the minimum error bound. So, what happens here? A 1 is added to the LSB position of the bits to be retained if there are a 1 in the MSB position and or subsequent bits which are being removed have also 1s. That means, if I am removing 3 bits, if the number is say 1 1 0 or 1 0 1, what shall I do? I add 1 to the LSB of the retained bits. What is the difference with the previous method? In the previous method, I just set it to 1. In this case, I add 1 to LSB. Okay. And if I have the bits which I am removing, let us say 3 bits, and they are 1 0 0, then what do I do? I actually add 1 if LSB is already 1, okay, and otherwise I make it, keep it 0. That means, what I am doing? I am trying to make the LSB always 0, that is an even number. Okay. So, effectively, if I take a decimal case, you will find that this is a kind of, if it is I am adding 1 to the retained bit when it is, that is 1 0 0 and 1 0, I am not doing it just for 1 0 0, I am doing it for 1 1 0 and 1 0 1, and I am adding 1 to the LSB. So, I am approximating the thrown away bits by adding 1 to the previous retained bit. Okay. If it is 100, it is actually a tie. It's actually a tie in the sense that if it is a 0.5, if I'm just throwing away in case of 0.335, and if I'm throwing away 5, whether to make 3 to 4 or keep 3 as it is. What we do? We take it to the even number. So effectively, I am resolving ties in favor of a even number. Otherwise, I am adding 1 to the LSB if I have got the bits to be thrown off greater than 100 or 01, the condition wise 100, etc. If it is not so, I am not adding anything to the LSB. So this is a rounding method, and if I compare this, why I have talked about all these rounding methods? Simply because you can realize that if I am implementing this rounding, this introduces additional computational requirement, and I need to have additional hardware in the DSP to implement this rounding algorithm. On the other hand, the other rounding, if you look at chopping, chopping is the simplest with almost no hardware requirement for the purpose of doing the approximation. So obviously these demands put in requirements of additional hardware on the processor, which can be used depending on the kind of instructions you are using, and also the kind of processes that you use determine what is the actual methodology being adopted. So here what we are looking at is a kind of an organization in this case. So I have got a multiplier and ALU, and this accumulator has got a guard bit, which is maybe an 8 bit. So I am just giving you an example of a Motorola DSP. We shall see more such examples, which has got, if I am doing a 24 bit into 24 bit, I shall get a 48 bit product, but I have got a 56 bit accumulator to have the guard bit. And if I am doing in a continuous sequence of computations, these guard bits provide for higher accuracy. Okay? And then when I am storing the value from the accumulator, I shall be using an appropriate rounding method and store the result in the memory. If I really do not have the accumulator guard bits, what I shall do? Here I shall do the shifting and rounding. So the round shift block which I am showing here, it is basically shift and rounding block. So whatever algorithms I have talked about rounding, that gets implemented in this block, because the multiplier is producing the output, that gets appropriately rounded, and then through ALU it is added and the result is stored in accumulator for multiply and accumulate sequence. So these are the two basic organizations taking into account the precision and the rounding in picture. So next look at the memory organization part. FIR tap implies multiple memory accesses. We have already seen that, because I need the data, I need the coefficient, the data sample that which is coming, as well as the coefficients. And DSPs want therefore multiple data ports, and in fact you will find many DSPs having multiple data buses and multiple data memories. And many DSPs implement what are called ad hoc techniques to reduce memory bandwidth demand. One is instruction repeat buffer. So instruction repeat buffer is what? I can put a set of instructions, and if these instructions are repeated, then I need not go back to the memory to fetch the instructions. So I have already fetched the instruction, put them in a buffer and execute them in a loop. So obviously this would reduce the loop overhead, and that this design issue comes up from the demands of repetitive numeric calculations of the DSPs. Often this resolves interrupts, okay, and thereby increasing the interrupt latency. This trade-off is an important point to note. Many of the recent DSPs have instruction caches, and these caches also allow programmers to lock in instructions. That means these instructions would never be removed from the cache, because they are to be repetitively used, and this cache memory turns into a first program memories. No DSPs typically have data caches. Why? Because the data is coming in a sequence, or it is already stored in a buffer and to be applied in a sequence, and same data is not expected to be used multiple times. So, data caches you will not find commonly in the DSPs, but you will find multiple data memories. So, what are the different addressing modes these DSPs use? They have standard addressing modes: immediate, displacement, register, indirect, and they would like to keep the MAC data path busy. So, that is, MAC is a dedicated hardware and which is involved. So, there are data flow through this path, and any instructions imply clock cycles of overhead in a loop. So, that may reduce the efficiency with which the MAC gets used. So, you can use the complex addressing modes, but for complex addressing modes, the basic tendency is not to use the data path. So, the data path is primarily targeted for data manipulation, and address manipulation can be done through auxiliary computation units. This is a basic motivation in designing the hardware for implementation of addressing modes. So, these kind of addressing modes are available: auto increment, auto decrement, and you can do it before actual operations or after actual operations, and we have discussed this kind of addressing modes in the context of ARM, and you can realize why ARM implemented this to facilitate this kind of sequence of data access, because here what is happening, you are actually getting a sequence of data from a sensor. Okay. So, to access this data in a sequence, this kind of addressing modes are really useful. You also have buffers. Okay. So, when you are doing with continuous IO, you would like to save the data samples in the buffer, and there has to be a logic implemented to avoid overhead of address checking instructions for circular buffer. Now, why would you like the buffer to be organized as a circular buffer? Because it is a continuous data flow, and you cannot have an infinite sequence of memory locations, you cannot have an infinite buffer, you have to simulate an infinite buffer. So, you use circular buffer to simulate an infinite and continuous flow in of data samples. So, you keep start register and end register per address, okay, using auto increment addressing modes. So, if you have this, then this can be very easily done, easily help you in implementing the circular buffer. And what you do is other option, there are two options for implementations. One is you keep start register and end register, and when you are using registers for auto increment addressing, so automatically you check whether you have reached the end or not. So, how to deal with the next address, and keep a buffer length register. In that case, so you have a start address and you keep a buffer length register. So, using this you can manage basically circular buffers. So, that is why we say that each DSP has modulo or circular addressing. This is a distinct feature of the addressing modes of the DSPs. You will not find this kind of modulo or circular addressing mode available with general purpose processors, and this is implemented through these kind of options, either having start and end register or having a start and a length register. And all checks here in this case for implementation of circular addressing is implemented in hardware. For execution control, you have hardware for fast looping, and you would like to have zero overhead looping, because loops are omnipresent. You have to do a number of numeric computations on the same set of data, on same set of operations on different data. So, for zero overhead looping, you may have actually I have already talked about the instruction buffers. You may also have counter registers to keep track of how many times the instructions, a set of instructions are getting executed. You have got fast interrupts for IO handlings, because if you are really handling each sample, okay, you are reading in each input sample via interrupt driven IO, you need to have fast interrupts. And this is related to the real time constraint that I was talking about because of the nature of the signals that are coming in. In fact, you have got basically two options available with you. One is called stream processing, another is called block processing. So in a stream processing, the processor completes the operations within the sampling period itself. Okay? So you make sure that you get a sample, do the operation before your next interrupt comes in to read in the next sample and do the processing. So this is your stream processing. And in a block processing, you read the data, buffer the data, and use this kind of an auto increment addressing to get the data from the buffer and do the processing. Also, many of the cases you have debugging support in the hardware itself. In fact, this point we have seen with other processors also, which have been designed for embedded applications. The specialized peripherals, you will find various kinds of serial ports and parallel ports for input of the data, on-chip AD and DA converters, timers which have got the universal role or any kind of processors, on-chip DMA controller for first memory transfer of data from one memory bank to another memory bank. Now, with this coverage of the general features of the DSP, we shall see how this has been really realized in some of the specific family of the DSPs. We shall look at TI as well as that of Shark family. These are from two different manufacturers. Now, in case of C5X, this is a family of DSPs from TI. They are primarily fixed point processors. So, if I want to deal with real data, I have to use QMN format, and there is support for this QMN format data. This is a modified Harvard architecture. There is only one program memory bus and 3 data memory buses, and this is a very interesting and distinctive feature of this processor. It has got 40-bit ALU and multiple implementations, either 1 or 2 instructions per cycle. It is not that all instructions of a single cycle. These are examples of 2 such processors, C5409 and C5510. So, in fact, 54 and 55 again refers to 2 distinct families and variations in the architecture. Let us look at now 54. So, 54X architectural features. It has got a 40-bit ALU plus barrel shifter, multiple internal buses, 17x17 multiplier, 2 address generators with dedicated registers, compare, select, store unit. And these are, you will understand why these things are obviously provided, and 2 address generators so that you can have multiple operands coming into the coming in for execution. Compare, select, store is you can compare basically the words, high words with the low word, and you can select the higher one to store if it is so desired. This is required for some of the signal processing applications, particularly applications for Viterbi coding. I shall not go into details of Viterbi coding, but this is a dedicated hardware targeted for those applications. In fact, 40-bit ALU performs 2's complement arithmetic and logical function, and it supports 2 16-bit operations in 1 cycle. In fact, your ALU is basically targeted for 32-bit operations and 32-bit word. In fact, 40-bit ALU which provides for 8 guard bits. Okay? But this 32-bit ALU itself can be considered as 2 16-bit ALUs. So, you can have 2 16-bit operations in parallel. Okay? Support saturation and sign extension. Saturation is a requirement for all signal processing operations. Inside, these accumulators are therefore partitioned into lower 16 bits, upper 16 bits and 8 guard bits. And the 17x17 bit hardware is associated with a 40-bit adder, and this 40-bit adder is distinct from ALU, so that you have got an independent MAC unit which is different from that of your ALU. This output of adder is passed to a unit that detects a 0 or an overflow, and so that it can perform saturation or rounding according to the mode or the instruction that is being operation. So this gives you a diagram, an internal organization, and you will find that the complexity in the data path which is there. It has got two accumulators, okay, and you will find that let us look at this part where you have got this multiplier. So, you have got this 17 cross 17 multiplier, and this multiplier on its path itself has got an adder. This adder is distinct from that of your ALU, okay. And these result, the other operand for the adder can come from any of the accumulators. These accumulators, accumulator A and accumulator B, there are two accumulators, and then this adder, output of the adder passes through 0, detect or saturation or rounding block. In fact, the hardware that I was talking about, this is a special hardware block which passes through, and then it can be stored back to an accumulator, or it can be stored back to the memory also. Okay. This is a special compare select store unit which can look at the data and select MSW or LSW, which the word to be select depending on the size. I said that I can compare the most significant word or the least significant word, find out which was the bigger, and I can store accordingly. Okay. This is a barrel shifter which can do the basic operations with multiplications and other things. So, you will find that it has got a pretty complex data path, and its address generation unit is different, which we call dgen. Okay. So, this address generation unit generates address and it flows through a number of buses, and here I have just shown the two bus, data read bus and two buses, these data read buses. Okay. And there are other buses. In fact, if I have a multiple data memories, there will be multiple buses available for these operations. The instruction sets obviously would support MAC and other operations, arithmetic operations, but what is interesting is these unique features, repeat and block repeat instructions. That is, I can actually repeat an instruction, and that repetition is completely supported in hardware. Instructions can read 2 or 3 operands simultaneously. This kind of things is not typical of any of ARM because it was primarily designed as a RISC processor. You can do a conditional store depending on a condition where and how to store the data, that can be specified as part of the instruction. And there are provisions for instructions so that you can return first from the interrupt. If I am returning first from the interrupt, obviously my interrupt latency and the accuracy of the timing behavior of the interrupt routine is guaranteed. There are some registers I am talking about. There are a number of registers to support arithmetic operations and other memory access, but the interesting thing is there is a circular buffer size register which enables you to implement circular addressing that I was talking about. Block repeat registers which tells you that the instructions and how many times they are to be repeated. Obviously, interrupt registers are there to take care of their control and masking conditions, and processor mode status register. It is a pipeline processor because obviously any today's modern DSPs, just like your general purpose microcontrollers which are targeted for embedded systems, here also I shall have a pipelining because pipelining increases the instruction throughput. In fact, it has got this what we call a program prefetch, the send PC address on program address bus. Fetch is load instruction from program bus to instruction register, decode. Then you have got an access block, put operand addresses on buses because these operands are being also obtained from memory. It is not just there inside the register. And then you read, get operands from buses and execute. You can understand the basic difference with the say ARM pipeline. In the ARM pipeline, the operands were typically as part of the registers. So, there was no pipeline stage for getting the operands from memory. In this case, you have got, because you will getting a sequence of data values maybe in a block processing mode which is stored in different data memories. So, you put operand addresses on bus and then get operands. So, these two stages comes into the pipeline. It also provides for power efficiency what are called power down modes. In fact, we shall discuss about these power down modes in more detail when we look at the power management aspects of different processors subsequently. This is just listing that it supports 3 power down modes: idle 1, idle 2 and idle 3. In fact, shuts down the CPU, shuts down CPU and on-chip peripherals, and shuts down the chip completely. I hope you remember the clock example we discussed with PIC, where processor CPU can be shut down, but the peripherals can work. So, similar kind of facilities are there with this processor. The most interesting feature of this is buses. The number of internal buses that it supports for accessing data in the program. Okay. So, I have got program read bus, data read bus, data write bus, and these are all address buses. So, you can see that since I have got these address buses, all these operations can be actually overlapped in time. And that is why if you remember the pipeline stages, I can have instruction prefetch, fetch, as well as data fetch, data address and then data fetch can be at different stages of the pipeline, because I have got distinct buses to transfer the data and provide the address. And this is a very interesting aspect of these DSP architectures, okay, the number of internal buses that are being supported. So, what we have got is, if you look at interestingly, when I am doing a program read, I have to provide address on this program address bus, okay, and I read the data on the program bus. This is what the instruction is coming along this bus. Program write is again providing the address on the same bus, because obviously you will not be reading and writing at the same time, okay. And if I am writing onto the program memory and I am using this bus. Data single read is here the address and here I get the data, and data dual read is I can provide the address in these 2 buses and I can get data in both these buses, okay. And I can also have, so this is what I am getting 2 operands on 2 buses simultaneously, and I can also get the data long read. So, there are other bus operations and modes as well. What I was interested to show you is that how the different buses the processor uses, okay, because it gives you a pretty efficiency in supporting what is called multiple memory accesses, because you would like to have multiple data points brought, multiple data stored, brought in, multiplied and accumulated, and this whole operation you would like to do in a proper sequence. And because of your demands of the data, you have got multiple buses over which these accesses can take place. So, you have separated out the program access, you have separated out the 2 data accesses, and so effectively you can have 2 distinct data memories and 1 program memory. So, these more or less brings us to an end of today's lecture. We have learnt about the basic features of digital signal processors. We have looked at one of these chips, C54X, in some detail, and we shall look at other DSPs, some of the other DSPs in the next class.